Okay, we've got a spreadsheet here which calculates the probability of profit. It's an example I'm showing. This spreadsheet's going to be available on my website in a couple of weeks as a turnkey spreadsheet. The first version will be you'll plug in your details yourself, and then I'll release one to use a Excel add-in which adds quotes, prices and other details to automate it. Anyway, more about that later. At the moment, I'm looking at XLF, the Spider's Finance Sector Index. End of yesterday, it ended at $37.86. And the strike is a put. I'm looking at 36. And these give me the likely outcomes. Now I'll just run through it. The probability of profit is 31%. The probability of out of the money is 68%. But because it's a strangle, the put is short, so that is my probability, 68%. Now if you're a put buyer, that is your probability, 31%. Now, these are the probability of touching, price within that time frame, 36 days. Now the strike price of the put is 36. The probability that the, well no, it's actually not touching, it's the probability that at the end it will have reached the exercise. The probability is 69.76% that $36 will be under the that the closing price of the stock will be above the $36 strike, and 30.24% that it will be below the strike. And that's normally distributed version, and that's a T distributed with 6 degrees of freedom version. Now we'll look at that in a minute. Now the range for the normal distribution version is $34.90 to $40.41, which is about $4.34 or something, I calculate. It's not a big range. It's not even though volatility is high, the overall volatility index is only 17%. So it's not that high. The implied volatility is about 21%, which I put on the call, but I'm using the extreme volatility measure here for the put because I'm a risk management freak and I'd rather the worst case scenario. Now that's a quick and dirty worst case scenario. Now that's a statistically derived VAR estimate. It's not an empirically derived CVAR or extreme value estimate. I'm not sure what the empirically derived estimate is, but you know that you can lose almost half your value in one single day. I assume that that's pretty extreme. So yeah, in my next video I'll discuss why that's important. And that's extreme value volatility, which I'm using as the implied volatility measure. It's higher. It's taken from the max high, max low in 12 months. Anyway, there's the, you can see there's not much difference between the T distribution and the normal distribution. The T distribution is a bit broader and a bit riskier. When you look at the overall range, it's quite significantly different. 29 to 44 as opposed to 34 to 40. So yeah, I know that I haven't looked at the distribution of this, so I don't know whether it's approximately normally distributed or that it's better fitted by a T distribution or some other distribution. Generally, for the sake of convenience, you fit with a t-distribution if it doesn't fit too well with a normal distribution. Although log normal is a possibility. It could be log normally distributed, but anyway, we'll change the subject. And this is a threshold. Threshold 68%, that'll turn red, which is a warning sign. Even though it's above 50%, I still don't consider that it's likely to finish in the money for the simple fact that it's 40 days out. 36 days out, sorry, which is a long way away. You can move a lot in that time, and that's another reason why I need to take that into account for the next video on how to set your stops for danger. Okay, so the put's expiring at 36, stock price is there. I think that's about all there is to see in this video. That's merely the time standardized into a decimal. It's needed for the Black-Scholes equation. I actually didn't use it for the delta there. I just took the delta from Tasty Trades page. It's close enough. I'll just explain these. Now, that's the delta formula, and it's very close to the probability of profit formula. The two are very close at the moment, as you see, 31 and the delta 24. It's still not that close. But anything over 3% interest rate, it gets more significantly different because the interest rate's a different factor, and the delta of the interest rate's added to the standard deviation. In the probability of profit, it's subtracted from the standard deviation. So yeah, you can see that with a higher interest rate, they become less at parity and less. You cannot use delta as a quick and dirty rule for probability of profit, although it does provide the likelihood of expiring in the money, but it doesn't necessarily give you a probability of profit. Only with low interest rates do they approximately match. All right, I think that's enough. Okay, I'll stop it here.